Pisa, 1583. A bored teenager is sitting through a long church service, and his eyes drift up to a lamp swinging on a chain. Big sweeps, then smaller ones as it settles. And he notices something odd. Timing it against the only clock he's got, his own pulse, every swing seems to take exactly the same amount of time. That teenager was Galileo. And the thing he spotted has a name: isochronism. Cut the swing in half and it still takes the same time. Wide arc, narrow arc. The clock doesn't care. So here's the natural question. What actually sets that time? What decides how long one swing takes? Let's list everything the period could possibly depend on. There's the period itself, call it t, the time for one full swing. The mass of the bob. The length of the string. Gravity pulling it back down. And the angle you start from, the size of that initial swing, which we'll call theta naught. 5 suspects. That's the whole cast. Now the trick behind all of this. Every quantity is secretly a recipe of just 3 ingredients: mass, length, and time. The period is a time. Mass is mass. Length is a length. Gravity is a length divided by time squared. And the angle? It's an arc over a radius, a length over a length, so it has no units at all. It's pure number. And this is where a beautiful piece of machinery kicks in, the Bakingemova Pi theorem. It says, count your quantities, count your dimensions, and subtract. We've got 5 quantities and 3 dimensions. 5 minus 3 is 2. So no matter how messy the true law is, it collapses down to just 2 dimensionless groups. So what are those 2 groups? Solving the little system of exponents, the first one comes out clean. Period squared times gravity divided by length. Check the units: time squared times length over time squared over length. The times cancel, the lengths cancel, and you're left with pure number. Beautiful. And the second group? It's almost a joke. The angle theta naught is already dimensionless, all by itself. So it just is the second group. Nothing to build. 2 clean numbers. And the whole physics of the pendulum has to live inside the relationship between them. But wait, look who's missing. The mass. It's nowhere in either group. And here's why. Mass is the only quantity carrying the ingredient of mass. There's nothing else with a stray kilogram to cancel it against. So it can't survive into any dimensionless combination. Which means, before we solve a single equation, the units already told us the period does not depend on the mass. Let that sink in, because it's genuinely strange. Hang a cannonball on the string or hang a cork. Same length, same swing, and they keep perfect time with each other. The heavy one and the light one, tick for tick, forever. Your gut says the heavy bob should swing differently. Your gut is wrong. Now 2 groups, 1 relationship. The theorem says the first group is just some function of the second. Rearrange it and the period pops out. T equals the square root of length over gravity, times some function of the starting angle. The theorem nails the shape of the law, it just can't tell us that leftover function. For small swings, we can pin that function down. The period is an even function of the angle, swing left or right, same time, so its odd terms vanish. Expand it, and for a tiny angle it flattens to a constant a. And the exact answer from the full physics is a equals 2 pi. So the period is 2 pi times the square root of length over gravity. And the shape is exactly right. Double the length and the period grows by the square root of 2, not by 2. Plot period against length and you don't get a straight line, you get that gentle square root curve. Galileo saw the pattern. And in 1656, Christian Huygens took it and built the very first pendulum clock, the most accurate timekeeper the world had ever seen. So that's the quiet magic here. 5 quantities, 3 dimensions, and the units alone told us the shape of the law, and that the mass simply doesn't matter. Now take that exact same trick and point it not at a swinging lamp but at a nuclear fireball. And it hands you a state secret. But that's a story for another day.